Hunan and Mexico City. I'm going to talk to you today about rain in tropical land regions, in particular about monsoons. And this is really the North American monsoon right here, this region that we've outlined in white. This is something that in the United States, when we talk about the North American monsoon, people really think about New Mexico and Arizona, but it's really the Mexican monsoon. Most of the rainfall is here in this region. And what I'm showing here on this slide is a plot just a few days ago of what the precipitable water, it's the water content, all of the water vapor in the atmosphere vertically integrated, just a few days ago. And you can see that we have this really humid tropical region, and then this sort of tongue of really humid air that extends northward along the continent. And this is giving you an indication that right now is a really active time in the North American monsoon, the rainy season in northwestern Mexico. This is actually a plot of the climatology, the typical average rainfall during July and August over North America. And you can see again this intertropical convergence zone region, this rainy tropical band, and this extension up here over the west coast of Mexico. So when we talk about monsoons in North America, this is what we really mean here, this seasonal migration of the rainy region up along the continent. And this region has, this rainy season over Mexico is highly important socioeconomically. When it's too strong, it can lead to a lot of severe damage and deaths. This happened a lot in the 1980s and 1990s. This region of northwest Mexico is a primary region for irrigated grain farming. A lot of the agricultural sector in Mexico is highly vulnerable to extremes of precipitation, heat waves, etc., because they don't have good access to insurance and credit on those very small scales. So variations in monsoon rainfall have great economic and social importance. That relatively small region, though, in this area right here, when you look at a global scale, seems very tiny. It is nevertheless part of a migration of the band of rainfall that extends all the way around the world, back and forth across the equator in a seasonal cycle. So this is an animation of the precipitation rate. And you can see we're going here from December, January, when the rain band is mostly in the southern hemisphere, into the northern hemisphere monsoon season, back into the southern hemisphere summer and monsoon season. And this monsoon over Mexico, the rainy season over Mexico, is really part of this seasonal reorganization of the entire general circulation of the entire atmosphere. So it's really a global planetary scale reorganization of the atmospheric flow. And that is tied, that reorganization of the planetary scale circulation. We often talk about this as though it's separated into these different regional monsoons. We have here the North American monsoon, the South American monsoon. There's a rainy season here in northern Africa, the Sahel rainy season, the West African monsoon. And then there's also a seasonal migration of the rain band here over the southern part of Africa. We have perhaps the most well-known and maybe the most intense monsoon is in South Asia, the Indian monsoon, the entire South Asian monsoon. And then even the northern part of Australia gets most of its rain from this seasonal migration. So all of these regional monsoons are part of this planetary seasonal restructuring of the atmospheric circulation. And what I want to do in this talk is to really begin by presenting to you some fairly simple ideas for modern ways of thinking about monsoons, modern ways of understanding monsoons, modern theories for monsoons, which really get us away from the traditional idea that land-sea temperature contrast is what drives monsoons. That is really not what happens. These are not just giant sea breezes. I'm going to use that, present some of this theory to you, and then present to you some of the implications that might have for present-day, year-to-year variability, what determines if this year is a relatively drought year or a rainy year, and then future changes in monsoons. Might we expect to see abrupt changes or tipping points in rainfall? And what in particular are the changes that we would expect to see over the next century in the North American monsoon? So starting off, this is really a very common way of idealizing or conceptualizing a monsoon circulation in some sort of simple sense. We have here a latitude versus height schematic, and we see a continent that is off the equator in the summer hemisphere. So this is the northern hemisphere over here in July or August, where we are right about now. And you can see that you have clouds forming and rain falling in the ascending branch of the circulation. Air then flows across the equator at upper levels and descends in the winter hemisphere. So you have cooler air sinking, warmer air rising. As the warmer air rises, it cools adiabatically, just like air cools as it ascends over a mountain range. And water vapor reaches its saturation point, it condenses, and it falls out as rain. Now, you'll notice that I've been very careful about saying what causes this. One thing that you'll often read even today in introductory textbooks is that you have a land-sea temperature contrast. The land surface gets warmer than the ocean. That sets up a thermally direct circulation. That leads to condensation. And then the latent heating or the condensation of water in these clouds provides an additional heat source that then drives this whole circulation. So we actually know that that's not correct. We've known that for several decades now in terms of the people who work on theory of climate dynamics, but it's still something that's very widespread in terms of common thinking, even in textbooks, even in some of the scientific literature about these circulations. Really what I think we would all agree on is that these are fundamentally driven by a contrast in latitude of the insolation or the shortwave input to the atmosphere. In the summer hemisphere, the Earth is receiving more sunlight, more shortwave radiation than it is in the winter hemisphere. And so this latitudinal gradient in the energy input to the atmosphere is really what's driving this circulation. So this is really an energetically direct circulation where air is rising where it's getting the largest energy input, sinking where there's a smaller energy input. And so I'm going to
say one thing. I mean, you're not saying, you're not denying, or to say, like a better word, that there's a sea breeze that's initiated by the land-sea contrast.
We have sea breezes every day.
Right.
There is a sea breeze. The penetration scale of the sea breeze over a continent is usually pretty small. Right. It's not going to give you something that, it'll be 10, maybe a few tens of kilometers. It's not going to penetrate far inland. Right. And it's a diurnal time scale. Right. This is really a seasonal reorganization of the entire planetary scale circulation. Mm-hmm. Furthermore, the sea breeze really is driven by land-sea temperature contrast. Right. And I'll show you in a few slides that observationally we see monsoons get weaker when land-sea temperature contrast gets stronger. Okay. So what I want to do is get you thinking about the total, not just the energy content that's stored in temperature in a dry parcel of air, but I want you to start thinking about the total energy content. And this is a measure, this H. We're going to call this our moist energy content. And it represents not just the energy stored in the temperature. This is the typical internal energy when a parcel of air gets hotter, temperature is higher, we multiply that by the specific heat. This is, units of this are joules per kilogram per Kelvin. We add that to the potential energy. This is a gravitational acceleration times whatever height the parcel is. And then we have an additional component of energy that is the latent heat. So it's the water vapor times the latent heat of vaporization, that LV term. And there's actually quite a bit of energy stored in this latent heat term. The total energy content also has a kinetic energy term, a 1/2 mass times velocity squared. But that is so small compared to these other terms that we typically can neglect it to a very high order of accuracy. And this total energy content is important because if we think about what happens in cumulus clouds, they actually aren't a heat source for the flow. What they do is they just rearrange what component the energy is stored in. So if you take a parcel of air that is in the boundary layer near the surface of the Earth, this will be its energy content. It'll actually have a fair amount of energy if you're in the tropics where it's moist and humid. There will be a fair amount of energy in this latent heat term, this LVQ term. And if air rises in cumulus clouds, so say you have a convectively unstable day, there are thunderstorms, afternoon rain, a lot of these parcels will ascend, they'll go upward. As they rise, water vapor will condense. By the time they exit the cloud, high up in the troposphere, around 10 kilometers or so, pretty much all the water will have condensed. But as you take a parcel of air and lift it, energy is conserved, right? So that energy has to go somewhere. It goes into raising the temperature and helping the parcel move to a higher altitude. But at this high altitude in the cold upper troposphere, there's no water vapor left. It's all been condensed and rained out. And so this energy in the upper troposphere is basically equal to the energy in the lower troposphere, but the content has just been rearranged between two terms. If you take a parcel of air at a certain height then, you know that its density, which is related to the temperature, right? A warmer parcel, warmer air is less dense. So you know that your air at a certain Z will be warmer and less dense if it started off with a higher humidity down here, or a higher temperature. Does that make sense to everyone? Any questions? Feel free to stop me if you want. I'm totally open to taking questions. So this really gets into a modern way to think about one of the central problems of the dynamics of the tropical atmosphere is how to understand, how to think about the interaction between the very large planetary scale circulations, the wind patterns, and the cumulus convection, the very small scale release of latent heat that you get in the cumulus clouds. And what we find is that, just like on the previous slide, if we increase the energy content, this CPT plus GZ plus LVQ of air near the surface, say by making it more humid or higher temperature near the surface, in the upper troposphere, that'll be equivalent to increasing the temperature. Because in the upper troposphere, you have very little water vapor, so you can't move the energy content of the upper troposphere around by changing its water vapor content, because it's just so cold and dry up there. So we think of the cumulus convection, the clouds, as working very fast. So you could do something like perturb the energy content, the moist energy content of your air near the surface. You could make it more humid. That would make a cloud, an existing cloud, become bigger and more vigorous, lead to some rainfall. That latent heating, but just like you experience when you're out in a thunderstorm or something, right before it rains, you feel these cool winds. Has anyone ever been out in a thunderstorm and right before it rains, you'll feel this sort of cool wind starting? So those are the convective downdrafts. The warm, moist air went up in the clouds. The cooler, drier air is descending into the boundary layer and mixing in with what was previously moist and warm air. And so all that the clouds are doing is they're mixing that energy in the vertical. So then the air that had been very warm and moist gets a little bit drier, and the final state that you end up in is a little bit warmer and moister in the boundary layer, and a little bit warmer through most of the troposphere. And what is, sorry? Well, relative to your initial, so you start out by putting in a big anomaly of moisture in the boundary layer. That heats the troposphere, but then some of the cool and dry air from the troposphere moves down and removes part of the initial anomaly, okay? But it doesn't take you back to the initial place, because you just, if you put a bunch of energy into the boundary layer, convection mixes it in the vertical, and you end up with energy that's homogenized in the vertical. So both the lower troposphere and the upper troposphere are both a little bit higher energy content. Make sense? Okay. So this is sort of the fundamental postulate of this idea that convection is a fast process that's sort of roughly always in equilibrium. It keeps the boundary layer roughly in equilibrium with the temperature of the troposphere, or it keeps the energy content of the boundary layer roughly in equilibrium with the temperature of the troposphere. And by that equilibrium, I mean you can perturb one or perturb the other. You can perturb one, the other will respond. And when we look at I'm going to give you an example of how this works, because the real world is often very complicated, right? We have a lot of stuff going on in the real world. I'm going to show you a simulation of what this looks like in what we call a cloud resolving model. So this is a box that is about the size of a single grid cell of a typical global climate model. So it's around a couple hundred kilometers on each side, say 200 kilometers on this side, it's a 200 kilometer square, the height of the troposphere, 15 kilometers high, something like that. And this is a snapshot of the cloud field and in these gray white areas. And the colors here show the low-level moist energy content. And you can see, if you squint a little, you can see that the clouds are preferentially forming over these regions of high, low-level energy content. And what they're doing is they're mixing the air in the vertical. And so we can run, what we've done is we've run an ensemble of simulations with this cloud resolving model. The horizontal resolution of this is about 1 kilometer, so several orders of magnitude finer resolution than a typical global climate model, fairly small domain. And then we've perturbed the state of the system so that we get different near-surface moist energy content. And we've perturbed it by changing the albedo of the surface, changing the elevation of the surface, and then we've just plotted time averages over a couple months. Each point here represents a time average of the low-level energy content on the horizontal axis and the upper tropospheric temperature on the vertical axis. And so each of these points is one several-month-long simulation, and you can see that they all lie very, very close to this one-to-one line. And so this is indication that this idea that what convection does is it just keeps these two variables, the low-level energy content and upper-level temperature, it keeps them tracking together with each other, that actually holds in these high-resolution simulations of moist convection. And so when we use that framework to then think about monsoons, instead of thinking about this fairly complicated three-dimensional circulation, it actually allows us to reduce the dimensionality of the problem from 3 dimensions to 2 dimensions. So instead of thinking about x, y, and z, we can just think about x and y, really. Previously, we would have had to think about what does the entire vertical temperature structure look like. And now we can say, well, the temperature is going to be warmest throughout the entire troposphere in the same region where the low-level energy content is highest. So we can, in this convective quasi-equilibrium idea, it says that the maximum values of the boundary layer moist energy content is going to be in the same location as the maximum temperature in the upper troposphere. And the maximum temperature in the upper troposphere is going to be where the warm air is rising. And then you're going to flow away from that region, sinking in the colder winter hemisphere. And where the warm air is rising is where you have the convection, and what the convection does is it keeps this upper level temperature tightly coupled to the low level moist energy content. And so the theory then for a quasi-equilibrium monsoon is that you know that the poleward boundary of this cross-equatorial Hadley circulation, this meridional overturning circulation in the atmosphere, that poleward branch is going to, its limit is going to be very close to the maximum of the low-level moist energy content. So you have energy being pumped into the atmosphere from radiation at the top and from surface fluxes of heat and surface evaporation at the bottom. And then the circulation is transporting energy away. Moist convection is very rapidly vertically mixing energy content and the temperature as sort of diagnostics of what's happening and using them to understand that circulation. Okay, so this is the general framework that we're going to look in. This is something that is about what is going on with this in an energy conserving framework where we're thinking about what convection does with the circulation. And there are a number of things that we can do with this framework. One, we can look and see, does this actually hold up in observations? Do we have the maximum upper level temperature in regions where we have the maximum low-level energy content? And it turns out we do. This is a climatology for July of the entire northern hemisphere. The low-level moist energy content is shown in colors. The upper-level temperature is shown in the black contours. And you can see that the maxima in both quantities is really here over this South Asian region. And the maximum low-level moist static energy is this sort of tongue of air that extends across northern India, and then the upper level temperature is maximum there. This is really the South Asian monsoon. So the South Asian monsoon maximum during July. It extends roughly halfway around the planet. So it is a very large-scale monsoon circulation. It's a very large-scale, planetary-scale imprint on the thermodynamic structure of the entire troposphere. The North American monsoon is a lot weaker, but you can see this low-level moist static energy maximum hugging the northwest coast of Mexico. It also has, you also have high energy content, humid and warm air over the Caribbean Sea, and they cause this not a true maximum in the temperature field, but sort of a ridge that they sort of deform the temperature field so that this maximum kind of gets pulled poleward and inland over Mexico and North America. When we look at that at higher resolution, this is the same quantities, upper level temperature shown in green, the low level moist energy shown in colors, and you can really see that the North American monsoon, just like the rainfall, extended in this tongue along the maximum energy content.
Excuse me.
Yeah.
When you compute the moist static energy, do you choose a height just above? I mean, following the terrain,
yep.
Or what?
These are all computed from this calculation that I'm showing you here is computed about 20 hectopascals above the surface in a terrain following model.
All right.
Yeah. And you do have to be careful about that. I've seen plots where people show these sorts of quantities on the 1,000 hectopascal level, where a lot of reanalysis products extrapolate data, and you get really wacky results that are not physical. So yeah, that's an important thing. Yeah.
So one difference in your previous map is that in the high Himalayas, the HB is high, and here in Mexico it's not.
Yes.
Right? I mean, because the maximum in...
No, not exactly. So you're almost right, but the Himalayas are actually right about here.
Whatever. But way inland compared to the Sierra Madre Occidental.
Although I would argue it's not that different, because I think that remember that the Sierra Madre Occidental are right here, right? So over Mexico...
Closer to the coast, actually,
Yeah. But still, over Mexico, you have this maximum energy content sort of going up and hugging the base of the topography, right? over South Asia, Himalayas, are right at the poleward edge of this tongue of high moist static energy air that is sort of lies inland over the very low-lying Indo-Gangetic plain. So I would actually argue that they're not that different. You know, in both you could. There's a difference in where there's land and where there's water, but in both regions you have high moist static energy air sort of forming at the base of this high topography.
Yeah. And why do you don't see it on the Gulf Coast?
That is, why don't you see? Well, you do see a maximum.
I mean, we call
here.
only the northwest monsoon.
Yep. Yeah.
But we don't call it monsoon on the other side?
Right, we don't call it a monsoon on the other side, although...
Not if you know what you're talking about.
yeah, although, you know, and this is speculative, but in Asia, we have the East Asian monsoon, which is a little bit more related to extratropical dynamics. It's not really thermally driven Hadley circulation dynamics. And I would actually argue that a lot of speculative, but in Asia, we have the East Asian monsoon, which is a little bit more related to extratropical dynamics. It's not really thermally driven Hadley circulation dynamics. And I would actually argue that a lot of what goes on here over the eastern part of the US related to maybe some of the Gulf of Mexico dynamics is a little bit more like what's happening over China and East Asia. There's a little bit more mid-latitude stuff that comes into play, so, which would be a separate talk. Okay. Yes.
I have another question. Do the monsoon usually occur in the Gulfs? For example, Gulf of Mexico, Gulf of Bengala, Gulf of Tonkin.
Do they usually occur in gulfs?
The Gulf of Bengala. The Gulf of
Right, the Bay of Bengal is right here, and really the rainfall maxima of the South Asian monsoon
is
here.
Between China and Vietnam, the Gulf of Tonkin. There's another monsoon, and another monsoon is between Gulf of California in Mexico and Gulf of Mexico in the United States.
They do, except for the fact that the African monsoon is really a moist energy maximum that does lie squarely over the continent, and that occurs in South America too. That during austral summer, the moist static energy maximum is really squarely over the rainforest of South America.
Thank you, sir.
Okay, so this behavior, this is a fairly fine scale feature. If we're talking about planetary scale circulations, one thing I'd like to highlight in the last part of my talk, I'm going to talk about global climate model projections for what will happen to this region in the next century. This blue box right here is a size of a single grid cell of a typical global climate model. This is about 2 degrees latitude by longitude. So if you want to resolve this sort of fine scale moist energy feature, or you want to resolve the Gulf of California, you're really going to need to use fairly high resolution models to be getting at this. So we're sort of moving into that era now where I think we can maybe say something about climate variability and climate change, but with a lot of the climate models we've had developed over the past decades, they really weren't so suited to this task. But okay, now let's get into implications. What can we do with this framework? Well, we can think about year-to-year variability. What does a strong monsoon year look like? Is it just a year when the land surface gets hotter than usual and therefore drives more rainfall? Well, no, it's actually exactly the opposite. This is a statistical composite, if you will. It's a regression of low-level moist static energy on rainfall averaged within this box, land rainfall averaged within this box. And you can see that this gives you a reconstruction of what the low-level moist energy field looks like during a strong monsoon year. And you see that the moist energy is really strongly elevated over much of northern Mexico here, indicating that the land-sea contrast in moist energy is increasing during strong monsoon years. Now, it's not because the land surface is getting hotter. This is that same statistical exercise done with temperature instead of moist static energy. So much of this North American monsoon region is colder the land-sea contrast in temperature has decreased during strong monsoon years. The way that we get higher energy content is the moisture content is higher. And it's higher enough, not in an energetically neutral sense, meaning that the energy reduction in the temperature component is more than compensated for by the increase in energy in the latent heat component. And then we can ask, well, what brings that about? That's an open question that I'm not necessarily going to answer here, but I think it's nevertheless powerful to know that you can't think about interannual variability in terms of land-sea temperature contrast. This is something that holds fairly universally across monsoon regions. I could show you plots like this for Africa, Australia, South America, North America, and this is another example for just the South Asian region. So here's India, right here. Here's peninsular India. And you can see that during strong monsoon years, southern India is colder than usual. This sort of Pakistan, Afghanistan region is hotter than usual. The temperature field is a little bit complicated, kind of hard to understand, well, what's going on here? When you look at the low-level moist energy content, you see, wow, the continental region has higher energy content than usual. There's an increase in the land-sea contrast of moist energy during strong monsoon years. So think of interannual variability in that sense, and then ask the question of what would cause a larger land-sea energy contrast in the total moist energy content. And that invokes questions of surface albedo changes, maybe SST changes, things like that. Horizontal advection. And that also holds up when you look at the onset of monsoons. So this is a composite of what the low-level moist energy content looks like during a late monsoon, a late onset of the North American monsoon. So in years when it's drier than usual in the early summer season here, in this North American monsoon region, you have this very broad region where there's low moist energy content. It's elevated higher than usual over this northern, very high latitude region, but in general, the land-sea contrast, Now, we can then get some insight into interannual variability, or at least show that this framework works in terms of interannual variability. Let's ask what's going to happen to monsoons in the future. That's what this last part of my talk is going to be like. I'm going to sort of divide that into two sub-points. One is, we want to know how will monsoon rainfall change in the coming century, right? We're in general seeing a trend of temperatures warming. What is that doing? There have been a number of papers published in some fairly prominent journals. This is PNAS, the Proceedings of the National Academy of the Sciences in the US, that have argued that once an anthropogenic forcing, CO2 or maybe anthropogenic aerosol emissions, once they reach some critical threshold, that monsoon rainfall will just shut down and you'll transition from a wet state to a very dry state. And this has been called a tipping point idea, that you can sort of push the system up to some point, it'll change gradually, then you'll reach some threshold and suddenly you'll shift abruptly into a new state. These papers have argued that they've even quantified this and said that for the South Asian monsoon, that once the top of atmosphere albedo, the reflectivity of the atmosphere, reaches a level of 0.5, the Indian summer monsoon would actually shut down within the course of a single year, and that Indian region would just transition to a dry state. You would no longer have a wet Indian monsoon. This may be something that has only been documented in a handful of somewhat prominent papers, but given the implications of this for billions of people on the planet, it seems worth investigating whether this might really happen. And what I'm going to do now over the next couple slides is show you that this idea is actually wrong, and that you can see pretty easily why it's wrong when you think in terms of this moist energy framework instead of in the traditional land-sea temperature contrast framework. So this idea of tipping points in monsoons comes about from thinking of this sort of feedback which can be represented, the details are not important, but you can represent it exactly in this sort of very simple equation. You don't need a complex climate model. You can write down a thermodynamic equation, a conservation equation for moisture, and a very simple momentum equation that just says if you have a gradient in temperature at low levels, say a land sea temperature contrast or gradient, you'll have a positive wind from the ocean to the land. That will generate rainfall. The rainfall will increase the temperature, which will lead to larger winds, larger advection of moisture onto the land, right? That sort of seems maybe plausible in some very hand-wavy sense. So you can take this system of equations and you can actually solve it. It turns out to be a system, there's essentially 3 equations and 3 unknowns. You can say, let's look for just the time mean solutions. So you neglect the time tendency terms. And then you can write down you can find a solution for the precipitation or the monsoon wind. And again, we're thinking of this sort of circulation, this rising branch of the circulation. The rain that occurs over the continent is what I'm plotting here in the blue line. The monsoon wind strength is what I'm plotting here in the red line. And this horizontal axis is the amount of energy being pumped into the atmospheric column over the land surface. So this is strong. It would be strongly positive due to the strong shortwave radiation absorbed during the summer season. If you were, say, to reduce the amount of absorbed solar radiation by increasing the reflectivity of the atmosphere, say by putting more sulfate aerosols into the atmosphere, more air pollution, then you would move down, you would move to the left on this curve. And according to that theory on the previous slide, you could move downward on this curve. Your rainfall would slowly decrease until you reach this very special point right here, at which point, if you go any further, you would decrease gradually until this point, and then if you go any further, there's actually no more circulation. Your monsoon just shuts down, it vanishes. People call this a bifurcation point. There's a whole bifurcation theory that you can write down for these sorts of things. But what we've seen is that this system of equations that I showed you on the previous slide, they were neglecting a few terms. They were neglecting a term which is associated with adiabatic cooling of rising air. So this W is vertical motion. This MS just represents the temperature stratification, or how much air cools as it rises. There's also a similar moisture stratification term. And what we can do is that if we take these 2 equations, the temperature equation, multiply it by specific heat, the moisture equation, multiply it by that LV latent heat term, if we add these together, we get a conservation equation for the total moist energy, just like we were talking about before. And we see that in those previous theories, they were neglecting a very important term. And when we put that term back in, we actually get this new system, or this new solution, that as you decrease the energy that you're absorbing over your summer continent, your rainfall does decrease, but it decreases smoothly just until you reach 0 rainfall, and then you stay dry. You don't have a point where we're going from 6 millimeters per day in your summer, bam, down to 0 suddenly, right? There's no threshold or tipping point or step function like response. And we can ask, well, this is a very, yes?
This is feedback is present over the Indian monsoon, but can we see it over the North American monsoon? Where is the overturning circulation?
Well, good question. This has been proposed or discussed really for the South Asian Indian monsoon, but this system is so simplified, so idealized that this could be any monsoon, right?
Yes. But over the South Asian monsoon is clearly seen. It is this feedback.
Sorry?
It is proof that this feedback is okay for the South Asian monsoon.
Nope. This is just, these are really very simple mathematical models, right?
But it has to be proved with data.
There's observations, and then there's trying to show You know, a system this simple, mathematical system this simple, it can be, you can have a lot of arguments about, well, how closely does this relate to observations? Which system is correct, right? So you can have arguments about that. But that brings me to that, I think my next slide will answer your question, which is, if we look at a model that is much more sophisticated, that has much more realism, and we try to connect these very simple mathematical models to a more realistic model. So let's go to a global climate model and say, can we find any evidence for this sort of tipping point in a realistic global climate model? And then we can connect it to a particular region. So we've done that here, not for the North American monsoon, because that's not what the debate was really a little bit more in the context of the South Asian monsoon. But it's a debate that there would be implications for any monsoon if that tipping point was found to be true. So,
but it is true that stronger the precipitation is, the convection is, higher latitude release, and stronger the overturning circulation. This is true for the South Asian monsoon.
That is true, although you phrased it as though the latent heat release causes the ascent. This is the classic chicken and egg problem, what we call chicken and egg problem. That you could also say the stronger ascent causes more latent heat release, right? And which is true. And what this whole quasi-equilibrium framework, what that shows is that if you create an anomaly of latent heating, that anomaly will last for 2 or 3 days, and the ascent anomaly will last for 2 or 3 days. And what the fundamentally important quantity is it's the energy that you're pumping into the atmospheric column. And then you can look at the energy content of the column, the moist energy content. So don't think about latent heat release as being causative. Think of the latent heat release being like the axle on the car, right? You know, you could look at, say, oh, the axle on my car is spinning, right? Therefore, it's causing my car to go forward. No, the burning of gasoline in your car engine is causing the axle to spin, right? And that's causing the car to move forward. So, convection is a very fast homogenization of energy in the vertical. It doesn't drive this planetary scale circulation.
It's a feedback. But it's a feedback.
Not necessarily, no. And I can show you different cloud resolving model simulations afterwards where if you put in an anomaly of moisture, you'll create an anomaly of latent heating. There will be a positive feedback that lasts and then it'll just die out. So if there's a positive feedback, it gives you 1 to 2 days. It does not create rainfall for a whole season. Yeah. But I think you raise a good point of like these are very simple theoretical arguments. If we look at this in a much more complicated and more realistic climate model that has realistic land-sea contrast, parameterizations, etc., do we see any evidence for these sort of feedbacks and threshold responses? So what we've done is we've taken a climate model at a fairly high resolution, 1 degree horizontal resolution, and we've subjected it to a very large array of forcings. So this is not one climate model simulation, this is an ensemble of simulations where we've done one simulation with CO2 a quarter of today's values, another with CO2 16 times what it is today. So we're never going to see that large CO2 change due to human causes. And then we've done a bunch of CO2 values in between. Then we've separately done simulations where we've perturbed the anthropogenic emissions of sulfate and black carbon aerosols independently, going from a quarter to 16 times today's emission levels. We've varied the land surface albedo. And what I'm going to show you now is a synthesis plot showing you how the strength of monsoon rainfall changes in response to those forcings. This is an example of the rainfall change you get from just one of those forcings. This is CO2 16 times what it is today, minus the modern day value, minus the simulation of modern day values. So it's the rainfall anomaly you get when you increase CO2 dramatically. And this is the Asian monsoon, and you can see that blue is positive rainfall anomaly. You get much, much more rainfall. You're getting up to 10, 15 millimeters a day more rainfall than usual over this entire South Asian region in response to this very large greenhouse gas forcing. And I'm going to average rain in the entire South Asian region, in response to this very large greenhouse gas forcing. And I'm going to average rainfall over this box, and now show you a plot where we show as a function, as a base 2 log of the factor by which we scale the CO2 value. I'm going to show you the monsoon rainfall or the monsoon circulation strength. And we're going to just see, do we see any values where, suddenly we just sort of drop down to 0, right? We're going to look for step functions in this to see, are there any tipping points or thresholds? And what you see is that as you increase the CO2 concentration, there's a little bit of a nonlinearity, a little bit of a curve, but there's a fairly smooth increase in monsoon rain rate and a fairly smooth, nearly linear decrease in the monsoon circulation strength. And when we look at what happens when we make these very large changes in sulfate and black carbon aerosol emissions, we see that the changes are actually pretty mild in the South Asian monsoon rainfall. Decreases of 5% or so in response to very large increases in sulfate aerosol emissions. We get the largest change actually when we have a very large increase in surface albedo of South Asia. We increase its albedo from 0, we're absorbing all the incident shortwave radiation, to 1, where we're reflecting all the incident shortwave radiation. That's very artificial, but you could think of it as a very, very large land use change or something like that. And you can see that the rainfall goes through a very large decrease, but it's a very linear, smooth decrease. You're not sort of, at some point, kind of just dropping down to 0 once you reach some threshold of the forcing. So this is evidence that what I showed you in those simple models holds up in a more complicated climate model. Now, I'm going to end my talk by talking about using a realistic climate model and using these moist energy ideas to understand what happens in simulations of North American monsoon rainfall over the next century. And David, is there time? Should I work?
Where are you on right now?
5 out of 1?
Yeah, go for it.
Okay. So I'm going to revisit via this quote projections from the Intergovernmental Panel on Climate Change. And basically the state of the art has been that it is very difficult to simulate the North American monsoon in climate models because of what I told you earlier, that the horizontal resolution of a typical climate model, the grid cells are so large that you can't resolve the Gulf of California. These very fine scale features in the moist energy field, you just can't represent those well in a climate model that has 2-degree horizontal resolution. So it's been difficult to simulate many North American monsoon-related phenomena, and perhaps as a result, signals of precipitation change over the coming century in response to greenhouse gas emissions are not particularly consistent across models, even in scenarios where we have the highest greenhouse gas changes in the future. And so what we've done, because we have this problem that the climate models that have been used to study this North American monsoon region, because they aren't very good tools for studying this problem, this is really work that's been done, led by Salvatore Pascal at GFDL NOAA in Princeton. We've used a high resolution, a 0.5 degree horizontal resolution global climate model. And we furthermore applied fluxes of sensible and latent heat, salinity, and momentum at the ocean surface to correct any bias in sea surface temperature that the model has. So this essentially takes us back to an earlier era of climate modeling where they applied sort of flux corrections. But it's being done here to say, well, maybe, although getting away from those sort of flux corrections was a good thing, we actually, if we're looking at these fine-scale regional phenomena, maybe it's important enough that the sea surface temperature bias is reduced to get the right answer that will return to that. And you can see that this high-resolution model with very low SST bias, it actually does a pretty good job of simulating this fine-scale structure of rainfall in the North American monsoon. And this is the model result. This is a reanalysis plot of reanalysis rainfall and moisture flux in the vectors. And this is a particular land rainfall data set. You can see that the models, this model as well as reanalysis, are overestimating rainfall over western Mexico, but they're nevertheless getting this tongue of high rainfall correct. And it's much better than a typical global climate model, which you can see in this time series of rainfall averaged over this black box here, which we're going to call our North American monsoon domain. I'm going to show you later some transects along this magenta line. And you can see that the observations here are shown in red with an uncertainty bound. And a typical 2-degree climate model doesn't do bad, it doesn't do horrible. It has a seasonal cycle, it has a rainy season, but the rainy season onset is delayed, and then the autumn is much, much too rainy compared to observations. When we go to a higher resolution model, 0.5 degrees, the wet bias in autumn is reduced. The onset becomes much closer to observations, but you get the largest reduction in bias, and you end up closest to observations when you additionally flux adjust the ocean so that the SST bias is removed. And that's the black line right here. So I'm now going to show you projections of the response to CO2 doubling made using this model from which the black line is taken. And this is the projection using that high resolution bias corrected model. And this is the fractional change in precipitation over the next 100 years caused by a doubling of CO2 concentrations. And you can see that the red is drying and the blue is moistening. So over much of this North American monsoon region, you have a pretty strong drying. You're getting to 20 to 30% reduction in summer rain rates. In contrast, this is a low resolution model that has a much stronger bias in the modern day climatology. And if you ask, well, what's happening to this North American monsoon rainfall, you have some regions where it decreases, some regions where it's very weak increase. Not much is statistically significant, as indicated by these gray dots. And so you get, well, there's some seasonal changes, maybe different parts of the season, different regions, but not much coherent signal. And so one possibility, this is not really an argument, but we're just showing that when you look at this region with a high resolution model that has a very skillful simulation of the modern day, you get a pretty strong drying, and perhaps this is something that we should be concerned about. Now, why do you get the drying? Well, because the atmosphere is becoming more convectively stable. We can think about the buoyancy of a parcel. It turns out that the buoyancy of air, how much force it will have to rise upward with in cumulus clouds, is actually roughly equal to the difference between this moist energy content at low levels and a measure of the upper level temperature. And so if we plot as a function of latitude and height the change in buoyancy in this color shading, you see there's a very large region where you have these red colors, red and orange colors. This is the Sierra Madre. This is that north-south transect that I showed you earlier. You have a very large region over the Gulf of California and this northwest Mexico Sierra Madre region where the air becomes less buoyant. And we can think of that as due to the fact that the upper level temperature is rising more than the low level moist energy content. Now, why do we have this enhanced upper level warming happening more than the increase in moist energy content at low levels? Well, what Salvatore did was a series of additional model integrations where he broke down the different components that force regional climate in a warmer world. You can hold the sea surface temperature constant and just double your CO2. That gives you hold the CO2 constant, but you just uniformly increase sea surface temperature everywhere by 2 Kelvin, you actually get a fairly strong reduction in rainfall over land. And that is because the warmer sea surface temperature leads to more convection and more warming of the ocean. So over ocean, you increase your moist energy content at low levels. That increases your upper level temperature over ocean in quasi-equilibrium. That temperature signal spreads out in the troposphere, warms the upper troposphere over land, and that makes your troposphere over land more convectively stable, reduces the rainfall. When you both double CO2 and increase the SST, these two sort of add together roughly linearly, produce this blue bar. And then when you consider the effects of not just uniform SST warming, but sea surface temperature pattern changes, the fact that some parts of the ocean warm more than others, you see that those changes in sea surface temperature patterns are also important. Altogether, they give you roughly in the neighborhood of the full model response, which is this orange line right here. What the bottom line of this small ensemble of simulations is that the remote changes in sea surface temperature are very important. Okay, the direct effect of CO2 on the land surface is actually quite small and produces, if anything, a small increase in rainfall rather than a strong decrease. So this is the end of my talk. I wanted to just summarize the 4 points that I hope you'll take away. Maybe the most important point is that I'd like at least some of you to start thinking about, leave this talk and think about, well, maybe an important quantity to think about tropical circulations in terms of is the moist energy content of the atmosphere. That what convective clouds do, what rainfall does, is it vertically, on a very fast time scale, just a couple of days or so, it vertically mixes energy content between the low levels and the upper levels. And then you can think of the overturning circulation in the atmosphere, the Hadley circulation, the rising branch, and the rainfall maxima as being closely related to where the peak low-level moist energy content is. Variations in that moist energy content, often over land, are in the opposite direction to what the surface temperature does. So you often have higher moist energy content when you have cooler land surface temperature. And so that gives you a very different picture of monsoon onset, interannual variability in monsoons, and thinking in terms of this conserved variable framework, it also allows you to come to different answers when you look at systems that might be used to predict tipping points or threshold behaviors in monsoons, and it allows you to understand in sort of the response of convection, how stable the troposphere is to convection, why in a high resolution, skillful global climate model, we get projections of a monsoon drawing here in the North American monsoon region. So that's it. Happy to take
Thanks, Dr. Gus. Some questions, preguntas?
Hello, Will. Thank you for coming here to give us this nice presentation. I hope you, as I said yesterday to Anne-Marie from France, I hope you like our university. We can see that the most populated areas in the world are the same areas from of monsoon. Monsoon. So, do you think this is related, population to monsoons? And one theory is that you said that if albedo goes up, insolation goes down, and that could reduce or shut down the monsoons. And could be this a massive danger for these areas?
Yes, so first of all, the first part of your question, I am not a demographer. So I really don't have much insight into what led to the current human population density being what it is. But it is true that monsoon circulations deliver rainfall to billions of people, probably 4 billion people or so on the planet. When you add up Africa, Asia, North America, South America, there's not many people living in northern Australia. So the variations in monsoon rainfall is very, very important. The second part of your question was, are albedo changes important? And yes, that they are very important, very potentially important, and that was really what was behind these sorts of simulations we did, because when you input sulfate, SO4, aerosol into the atmosphere, sulfate is a very reflective aerosol, and so over Asia, there's been a tremendous increase in sulfate emissions over the past decades. And so the top of atmosphere albedo has increased in response to anthropogenic aerosol emissions. There's been a lot of studies that have attributed reductions in rainfall over central India to increases in anthropogenic aerosols. Those reductions have been on the order of maybe 5%, maybe 10%, 5 to 10% with a pretty big error bar. That's pretty consistent with what I've shown here. So, the CO2 changes that we're going to get are maybe doubling a CO2 moving from this point to this point. But in terms of anthropogenic forcings, CO2 may be moving from here to here. Anthropogenic forcings, we may have moved from pre-industrial here all the way out to this part of the curve. So we're accessing a much broader range of aerosol forcings. But also, I don't think that aerosols are not going to take you down to zero rainfall, at least from this sort of evidence.
So we don't have much to worry about.
I wouldn't say you don't have much to worry about. The modern day interannual variability of South Asian rainfall is plus or minus 10%. So a really drought year with a lot of heat waves, many people dying, 90% of typical rainfall. So relatively small changes on these curves could have huge socioeconomic effects. And we're talking about seasonal mean rainfall. We're not even talking about extremes yet. So there could be large changes in extremes too that I haven't addressed at all. Thank you.
Thank you very much for your presentation. Is this on? So I was, could we go back to your schematics about the circulation? Maybe it would be better to go to the last line.
I'll get the bigger one.
Perfect. So that more or less summarizes the way I think about the Hadley cell, right?
Yes.
So
yes.
For me, this is the Hadley cell, and when I think about monsoons, I mean, this is not my area of expertise. I think about land, and I think that is a point that I'm missing in this picture. So if we see the North American monsoon region, we see this tongue of high levels of moisture. The same thing happens in India, just south of the Himalayas. So how do we address that fact that for me is fundamental to monsoons? So for me, monsoons are relevant theoretically, because besides this schematic, which I agree with completely, we get this restructuring of what we would expect if we didn't have continents and contrasts caused by land. And I never, considering the previous illustration, I never thought about the monsoon as a huge sea breeze. I would never say that it's the land-sea contrast, but I do see value in considering those contrasts in how the sea responds, how the land responds to getting this type of circulations, which is precisely what I think I'm missing from this talk. So when I see the development of patterns in Mexico, surface pressure patterns, they do seem to organize along the line. You see streamlines following, organizing around the coast, and that does seem to have something to do with contrasts in temperatures, although it's not a sea breeze. So
Yeah.
So then,
well, let me maybe just before you go too far on, let me answer some of your questions.
Yes.
Before you, I tend to forget if we go. So the land surface is very important, but my point was that a traditional view of thinking about monsoons is that the land surface heats up, that somehow generates some thermally direct circulation and convection, and then the convection can somehow carry you forward through the entire summer season, right? If you think about the moist energy content and what convection, all that convection does is it very rapidly mixes it in the vertical, then you have to say, well, if I pump more energy into the atmosphere here over land, I'm going to have some convection, it's going to mix it, and the Hadley circulation is going to carry it away from the land surface. But I have to keep pumping energy into the atmosphere over land to maintain this thermally direct Hadley circulation. And so that's exactly what I'm arguing for, except that I haven't shown you the full, I haven't given a talk on the full energy budget. There's sort of an entire separate, once you're familiar with moist static energy view of thinking of things, we could sort of have another talk about the vertically integrated energy budget and think about the inputs, the sources and sinks of energy into the column. So over land, the land surface has a very, very low thermal inertia. If you average over timescales longer than 5 days or so, the land surface, whatever downward radiation it receives, it has to pump back into the atmosphere in the form of sensible linear heat flux. The ocean is enormous in comparison, has an enormous heat capacity. So the ocean can just, summer sets in, you start pumping radiative energy into the top of the atmosphere over land, short radiation, summer hemisphere. Your land surface then absorbs some of that, but pretty rapidly just emits it back into the atmosphere. So the atmosphere is being heated, right? There's an energy source. You're getting shortwave radiation over the ocean, but the ocean is just kind of buffering a lot of it. And so your energy source is much larger over land. That causes the energy content to rise to a high level over land, and you can maintain this, this maximum of moist static energy content over land. Going back to my schematic, you're basically maintaining this moist static energy maximum by just continually pumping energy into the atmosphere in the form of radiation. If you got rid of land, this maximum would stay near the equator, maybe move just a little bit because the ocean has a high heat capacity. If you people have done model simulations where they make the ocean very, very thin, and then you can get a large moist energy maximum that moves very far off the equator without land because your surface has a low thermal inertia. Right? In the real world, we don't have a thin ocean. We have a land surface and we have a thick ocean. Does that answer your question at all?
Yes, more or less, because I would think also transport would be fundamental at low levels. This really high moisture, for example, in here in the North American monsoon, you would need this. I mean, I think the problem is, and I was getting to this point, is thinking about once you have this set circulation might blur things up about how it comes about, because you were addressing right now how it comes about, but I would like to actually see, because you see the temperature over land and it's lower during very strong monsoons, but that's once you have all this going on. What happens at first, how it first establishes itself, how does this moisture transport from the ocean into the land play a role? So I think I was going towards that place, to seeing how it establishes itself, because if not...
So one caution that I would have, though, that I would give you is to not get too hung up on the details over daily timescales of the transport processes, that when you average over a month or so, when you're thinking about the seasonal mean behavior of the system, a lot of these transient eddies and advection, and a lot of them, there's a lot of compensation and cancellation, and you can get pretty far with some parts of the atmosphere. You know, if you think of the zonal mean atmosphere, you can actually get pretty far with a diffusive approximation for the energy transports, which just gets rid of a lot of the messy detail and, you know, to some degree throws out the baby with the bathwater. Yeah. But you know, it shows you that a lot of times these details of the transport can be misleading. But you're exactly, maybe I'll just close your question by just saying you're exactly right that this is what we call a diagnostic framework, right? Prognostic framework would be saying, give me the energy source and I'll give you the circulation, right? The problem with that is that we know the energy source is sunlight, right? It's insolation. In Northern Hemisphere summer, in June, late June, solstice, the peak insolation is near the North Pole, right? It's not at 23.5 degrees north, it's near the North Pole, peak diurnal mean insolation. So why don't these maxima move all the way up to the North Pole, right? Yeah. Because the ocean does a lot of buffering, you have zonal advection, there's albedo, high albedo and high latitudes, but then counteracting some of that, there are large feedbacks. You know, you're pumping energy in, but there's a greenhouse effect, water vapor greenhouse effect. There's clouds are trapping radiation. So the difficulty with the prognostic frameworks is that if you give me the energy source, the circulation that I would calculate would be complicated by the fact that the feedbacks, greenhouse effect, albedo changes, etc., those actually turn out to be nearly as large as some of the forcings. So it's very much an open problem of how to solve that.
Okay, thanks.
¿Más preguntas?